Okay, can you see everything?
Yes.
Awesome. Okay, so thank you very much for giving me the opportunity to give a seminar about this. So I'm going to talk about signatures of AGN feedback on star formation at high redshift. And previously I did my PhD at Durham University, and I did also 1 year studentship at ESO. So if any student would like to do 1 to 2 years at ESO in Munich or in Santiago, please message me. I can give you some pointers or some information of how to apply. So first of all, I would like to give a quick outline. First, I'm going to talk what are AGN, why do we even bother? Then I'm going to talk about star formation rate distributions of AGN host galaxies and what we can learn with combining observations and simulations. Third one is then going to be actually directly observing AGN feedback, or trying to observe AGN feedback with ALMA and integral field spectroscopy, integral field unit. Quick side note, high redshift for me is redshift 1 to 4. Low redshift is anything less than 1. And very high redshift is anything bigger than 4. For me, that's like, oh my God, I can't even do IFU stuff. So, yeah. So first of all, what are AGN? They stand for active galactic nuclei, and they are basically accreting supermassive black holes. Their masses vary. So the Milky Way black hole has a couple 10 to the 6, like a couple million solar masses, 10 to the 6. The biggest one in like the most luminous quasars we can get is 10 to the 10 solar masses. But during a lifetime of a 10 to the 8 solar mass black hole, during this growth, it released 10 to the 54 joules of energy. Binding energy of a galaxy, the gravitational binding energy of a galaxy of roughly 10 to the 11 solar mass, like halo mass rather than stellar mass, is roughly 10 to the 52 joules. So AGNs and supermassive black holes have enough power to destroy the galaxy from inside. Now, we see galaxies at, local. We live in a galaxy, so obviously it doesn't do, but it kind of stands to reason that it must have some massive impact on, or it can have a potential to do a massive impact on the host galaxy. So how it can influence the galaxy? It can do it via radio jets, where we are talking of relativistic particles being ejected from close to the event horizon of the supermassive black hole. You can do gas outflows, where on the accretion disk level or something, there is a photon pressure that starts ejecting massive amount of material, and then slowly it goes to these hot ionized gas, to eventually even to molecular gas outflows, or those that are not very well understood. Also, another way to influence its host galaxy is just simply, it's a massive heater right in the center of the galaxy, and you need cold gas in order to heat up in order to have a star formation. So what happens if you start heating, if you have a massive heat source in the middle? So there are a couple of connections between AGNs and galaxies. For example, they grow at the same time. So this is sort of equivalent of the Maddow plot, what Bitten showed last week, where we have star formation rate density and accretion rate density on y-axis against the age of the universe, against time. And when you scale the black hole accretion rate density, which is the gray curve, the black and gray curve, by roughly scale 1500, then you realize that it has a very similar shape. It even peaks at the same time as star formation rate. So they have the same history. This can be very much explained because you need cold gas for both of them. So it's more of a signature of common fueling rather than any sort of feedback processes from the black hole. Another one is that when you look at the masses of supermassive black holes in low redshift or local elliptical or bulge-dominated galaxies, this is on the x-axis, and on the y-axis you have the mass of their supermassive black holes, you realize they are very tightly correlated. And again, this is used as one of the first observational evidence of AGN feedback. I would rather say it's another signature of common fueling, because you need to funnel cold gas into the center of galaxies in order to grow both the bulges and the supermassive black holes. The first, I would say, signature or evidence for AGN feedback comes from simulations, not necessarily from observations. And this is a sort of equivalent plot of the luminosity function experiment from Bauer 2016. You have the stellar mass to halo mass ratio on the y-axis against the halo mass. So that's the dark matter halo mass on the x-axis. And the galaxies are overall most efficient at actually having the most massive stellar masses for their halo masses, right around 10 to the 12 halo mass. And you see that in the green curve. What you can do with simulations that you can run simulations without any sort of feedback processes, either from star formation or AGNs. And that's where you get the gray curve right on the top. You see that you overestimate the number of low mass galaxies and high mass galaxies as well. If you say, okay, I want to see what star formation feedback does to the population of galaxies, then that's the purple curve. And you see that you reproduce the right number of low mass galaxies, but you have too many high mass galaxies. And for that, you need to include both star formation and AGN feedback, which is the black curve, in order to truly be able to reproduce the properties of the universe. Now, okay, so we know that in simulations, AGN feedback is essential in reproducing the properties of the universe. How do we actually study this? So one of the oldest one, where the papers go all the way back to 2009, is basically looking at very simple experiment. The more luminous AGNs are, therefore the more winds or jets, or they are just bigger heat source in the middle, therefore they should have bigger impact on star formation in their AGN host galaxies. So if we would plot sort of star formation rates of galaxies, AGN host galaxies, against their luminosity of the AGNs, usually we use X-ray luminosities because they are quite a good way to do this. Then we should see that if there is if AGNs are actually even helping the star formation, that we should go up. If there's some sort of negative feedback where actually AGNs are suppressing star formation, then it should go down. And you can see that we have radically different results. So on the top middle panel, that was actually one of the first page 2012 studies that there's there's evidence for negative feedback. Actually, they have only 6 sources in the high luminosity bin, where you see that arrow. And so it wasn't really, it was a small number of statistics. And quite a few times you see an uptick. So actually, the more luminous the AGN is, the more star formation their AGN host galaxies are. But this is where we get to the problem, how do you measure star formation of AGN host galaxies? Because every single time you want to do AGN host galaxy, you have to deal with that pesky AGN in the middle. So normally you measure the star formations, that you look at sort of the effects of the O and B stars, the young hot stars with a very short lifespan that have loads of UV, they emit a lot of UV photons, they ionize gas around. That actually is what the H alpha emission line is usually. But then also a lot of the time that all that UV and H alpha emission gets obscured by dust and re-radiated at near infrared. Problem with AGN that we can see on the left is that the accretion disk is emitting a massive amount of UV light. H alpha emission is also emitted because the UV light is ionizing the gas, so sometimes it's also quite a bad tracer. And also there's a dusty tori, like a dusty sort of structure around AGNs that usually block all that light and then re-emit it infrared. So if you look at the sort of SED, spectral energy distribution of an AGN and a galaxy, so you see the blue, for example, the blue line, that's your accretion disk, and that's from like optical to UV light, and you can see in gray curve that's actually an SED of a star-forming galaxy, and you can see that's actually quite it's actually contaminating all your UV light, so you can't measure effectively, or you have to be very careful about how you measure stellar masses. And then also you have the dusty torus, that's the red curve, and you can see that that's actually kind of going into this mid-infrared, near-infrared, and far-infrared stage, which is another tracer for star formation. So you always have to do a very serious SED decomposition to figure out what light is coming from AGN and what light is coming from your AGN host galaxy. And when Flora Stanley in 2015 did this on a proper large sample of at least 2,000 AGN host galaxies, so you don't have a problem with small number statistics, and you do a proper AGN to star formation decomposition, so you actually can properly see what light is coming from the AGN, what light is coming from the AGN host galaxy, then you realize that the mean star formation rate against, here it's plotted as instantaneous black hole accretion rate, it's basically your AGN luminosity, that it's quite flat. It's a flat trend. You have to be really bit careful that sometimes high luminosity systems are in high mass galaxies. So you have to account for that. But when Chris Harrison in 2017 in his Nature Review paper actually compared it to the Eagle simulation, which is one of the simulations I'm going to talk about later, it actually agrees relatively well. So even though the simulations require AGN feedback, you don't really see any trends of mean star formation rates against AGN luminosity. However, I kind of tried to stress as much as all these plots looked at the mean values, the linear mean values of the whole of your population, and that's not always the best way to measure differences in populations, because you can have two completely different distributions of some property, and they will have the same linear mean, but actually they are completely different populations. And first time this was shown in James Mullane 2015 paper, which was a pilot for my study, where he looked at the distributions of star formation rate of AGN host galaxies, that's the top plot, against the main sequence galaxies, which is on the bottom plot. And they have the same mean star formation rates. The both populate AGN host galaxies and main sequence star forming galaxies, the typical star forming galaxies. So the whole idea was AGNs are not star forming galaxies, and the whole idea was, well, is there a chance that even though we see a flat trend of mean star formation rates against AGN luminosity, can it be just because we are not measuring it properly? Is the linear mean just not sensitive enough to some subtle changes in the distribution? So we decided, okay, we have to look at actually the distributions of star formation rates. The problem with that is that in order to study your distributions, you actually have to detect significant portion of your sample, because otherwise you can't actually constrain the distribution. And with Herschel, which is most of these studies were with, you get around 5% detection rate. So you result in either stacking or some very clever statistics, survival techniques. So you need to actually use a telescope that's going to detect everything. And that's where ALMA came in. So we observe overall roughly 114 AGN with ALMA band 7 continuum. That's roughly 870 micron, roughly what that is, 870 micron band. And that's when you shift it to the rest frame, that's roughly 300 micron data point, which is perfect for determining your amount of star formation that you have in host galaxies. From that, we selected AGNs that were in 10 to the 43 to 10 to the 45 ergs per second. These AGNs are moderate luminosity AGNs. They are not these little things that you can barely detect, but at the same time, they are not like these rare quasars that you just never going to, that would just be very extreme part of the population. We look at stellar mass of bigger than 2 times 10 to the 10 solar masses. And the reason for this cut was that simulations are telling us that above 10 to the 10 solar masses, that's where you really see sort of where AGN feedback starts to be important. And the redshift range of 1.5 to 3.2 is because that's the peak of both accretion rate history and also star formation rate history. We are going to compare everything to Eagle hydrodynamical simulation. It's a state-of-the-art cosmological hydrodynamical simulation. The reason why we picked it is because it's in-house. It was actually developed in Leiden and Durham. So when we had a problem with it, or we didn't understand something, we just went to the people upstairs and we had coffee with them, which was very useful. They fully implemented AGN and star formation feedback, cooling mechanisms, and also it's quite a large simulation as well. So you get this decent amount of galaxies in them. It's actually 100 cubic moving megaparsecs cubed. The whole thing was calibrated. So you always need to calibrate your simulations, basically, because you can't simulate every single atom and molecule. So you need to sort of calibrate everything. And they calibrated on stellar mass functions, galaxy sizes, the black hole spheroid relation from Corbendy 2013 that I showed before, but not on star formation rates. So we can compare the universe, our observed universe, to this simulation. We can compare it at the star formation rates, and we know that it's not, they should not agree just because they calibrated, they should agree because the physics was right. The particle resolution was roughly 1 million solar masses. So each particle, the smallest particle in the simulation, was 1 million solar masses. So now we get to the, how do you estimate distributions? And ALMA is amazing, don't get me wrong. We actually got 38% detection rate from Herschel, which was like less than 5%. So it's amazing. However, in order to, you still with 38% detection rate, you can't actually look at the distribution of star formation rate or specific star formation rate, which is star formation rate normalized to stellar mass, directly. So first of all, you have to assume some sort of, what sort of shape of the distribution it is, which we assume it's a log normal distribution that came from Eagle, that came from that galaxy, star forming galaxies actually have a log normal distribution of star formation rates. And then we use this hierarchical Bayesian method with Gibbs sampling. It's an MCMC chain where we basically draw from some posterior distribution what the shape and width of the mode, which is the most common value, and the width of the distribution might be. And from that, we did a number of tests with Eagle simulation where we changed the detection rate from Eagle, and we did tests. If you have any questions, ask me after the seminar. And on the top right, on the bottom right, you actually have how it works. So the gray filled histogram, that's actually our detections. The outline of the histogram, those are the upper limits. And then what you see, the dashed black curve, that's actually the distribution that we got out of it, that we had a constraint. I would like to point out is that when we calculate the linear mean of our log normal distributions and we compared it to Flores 2015 work, we actually agree. So we agree with the past papers and the past works, but at the same time we are learning more, we are getting more information about the shape of the distribution. So here I'm going to look at specific star formations against X-ray luminosity, basically how star forming these systems are against X-ray luminosity. The black points are the data, the green points are actually the modes, so the most common value, the peak of the distribution for the two luminosity samples, the low X-ray and high X-ray luminosity sample. And you can see that there is like a 1.8 sigma drop, so barely anything. So what happens when you compare it to the Eagle simulation? Well, our high X-ray luminosity sample doesn't agree with Eagle, but then we realize this one thing. Every single time you do galaxy surveys, especially at high redshift, you are probing way bigger volume of the universe compared to what the simulation can do, simply because the simulations run out of memory soon. So we actually have way more high mass systems compared to Eagle in our observations. And when we mass match actually those two samples, then we realize that we agree quite well with Eagle. So Eagle really predicts that there should be a very flat trend of the distribution with X-ray luminosity. So we show that stellar mass is extremely important. All right, we needed to mass match actually our galaxies, our samples, in order to make a fair comparison. So what would happen if we would plot star formation rates or specific star formation rate against stellar mass of our systems? And there's like a 2 sigma drop, nothing really significant, 2.5 sigma, and Eagle agrees perfectly with it, right? Nothing unusual. And then we were like, okay, what about galaxies? And now I mean overall galaxy population, both quiescent and star-forming galaxies. And AGNs are a little bit more star-forming than the overall general population of galaxies, but that's probably because AGNs require cold gas supply, so you're more likely to have a star-forming system, but nothing really tells you about the feedback. So our observed AGN look like AGN in Eagle. Feedback is not seen in reduced specific star formation rate or star formation rate in luminous AGNs. So and we can see that in Eagle. So where is the effect of AGN feedback? It's supposed to be necessary in Eagle. And this is where there comes the beauty of working with simulations, because you can start playing with the simulations. And one of them is, I wonder what happened if you just switch out the AGN feedback and look at everything. So on top panel, you see the mode of the distribution, therefore the peak of the distribution, the most common value against stellar mass. And at the bottom, you see the width of the distribution, the specific star formation rate against stellar mass. Excuse me. And what you can see is that you see like that actually star formation rate or specific star formation rate is dropping a little bit faster with stellar mass in simulations which have AGN feedback, but more importantly, you see much broader distribution of specific star formation rates once you get along above 10 to the 10 solar masses in the Eagle simulation with AGN feedback. So AGN feedback is actually broadening the distribution of specific star formation rate. When you compare it to the AGN, they agree with the AGN simulation. By the way, we couldn't, by definition, compare AGNs in the non-AGN simulation because, by definition, you have no AGNs. And our observations actually agree with Eagle with AGN feedback. One might say, okay, what does it mean, broader width of the distributions? I need to imagine it somehow. So here you have a density plot of specific star formation rate against stellar mass, and in the red you see the non-AGN model, the non-AGN simulation, and in the blue you see the AGN simulation. And what you can see that the normal AGN reference model has these population of low star forming galaxies that you just simply don't see in the no AGN model. So the AGN feedback is responsible to creating this low star formation quiescent population. It would be worth noting that in the simulation, the individual galaxies are sort of traveling between those two, sort of the star forming state and the quiescent states. They actually move quite a few times. So the summary of my first part of the talk is we use two different versions of Eagle and ALMA observations to investigate the effect of AGN feedback. We see no evolution of specific star formation and distribution with AGN luminosity, but AGN feedback can be seen in simulations as a decline of specific star formation rate or steeper decline with specific star formation rate with stellar mass, and much wider distribution of specific star formation rate above 10 to the 10, more diverse galaxy population. And another main take for this is great things happen when you combine observations and simulations rather than sort of just competing on who can do it better. The big question is, how can AGN suppress the star formation, right? The most ideal way of testing this would be we map the star formation, we map the AGN-driven outflows or jets, and we place some constraints of, okay, can we see AGN outflows actually suppressing the star formation? Very good way of tracing ionized gas outflows is by O3 doublet at 507.7 nanometers. O3 is a forbidden line, which means that we can't actually make this emission line in labs because you need incredibly low density structure, because otherwise they de-excite the oxygen actually de-excites itself by collisions. And it traces 3,000 to 5,000 Kelvin gas, very low density, which is just like AGN outflows. It's brilliant. However, to map optical emission lines, we need IFUs, which is integral field units. because unfortunately this is not radio telescopes where with the antenna we can basically get also the spectral information, right? With CCDs you leave any sort of spectral information of your photons that you receive. You just get the total brightness. So what you have to do clever tricks, and one of them is the IFUs, where you basically slice your focal plane of your telescope using either lenslets, or you do it with lenslets that actually feed it to optical fibers that actually feed it to a spectrograph, or you have used tiny little mirrors to actually slice your field of view into individual what we call spatial pixels or spaxels, and basically those light from those spaxels can be then fed into a spectrograph, and then we can actually do a full spectrum of that pixel. The final output of the data cube of the pipeline is a data cube which has RA, DEC, and a wavelength or frequency or velocity axis, whatever you decide. So how do you map ionized outflows? Do you just look at the total, just look at the O3 profile? Not necessarily, because you can also have the classic gas that's just moving around, just like because of gravitational well, rather than actually any sort of moving. So what you have to do is that you search for these blue wings in the emission, and these blue wings of the emission line actually show trace high velocity gas that's moving towards you. There should be another wing that's where the gas is moving away from you, but since it's an optical line, it's actually obscured by the galaxy, so we only see the blue wing most of the time. And once you actually decompose, or what's the outflow, which is the blue shaded region of the spectra, and what is the sort of the typical galaxy emission, which is the red part, you can then create sort of velocity slices of your cube, and you get the two images. When you want to map unobscured star formation, you go for H-alpha emission line. It's quite good. It's easy to detect at a high redshift. The problem is that H-alpha emission line is also emitted by AGN. And then there's also a nitrogen doublet nearby, and they all blend together. So there are a couple of examples of spectra where you see the sort of very broad AGN line in magenta. Then you see the yellow emission line. It's actually the narrow H-alpha emission, which we actually want to trace the star formation. And then the green is actually the nitrogen that you also don't want to. So in order to do this, you need to basically go spaxel by spaxel and run the fit and completely decompose them. A little bit similar to what Hannah actually developed for her star formation regions a couple talks ago. So in similar practice. And you might say, it's like, yeah, and you have been talking about finding observational signatures of AGN feedback, but I'm pretty sure we solved it in like 8 years ago, right? So why are we still banging about this? These are 3 studies, one from Carniani 2016, Kresge 2015, and Canadias 2012. And the images are the narrow H-alpha emission that should trace star formation, unobscured star formation. And then in 3 cases, it's the white contours in the top right, it's the black contours which trace your outflow. And what you can clearly see is that where is the location of the outflow, you don't see any star formation. So you might like, yay, ionized outflows are really suppressing star formation. And we solved it. AGN feedback is solved. But I have a couple of questions. And it comes to the way you trace star formation, because at the beginning I showed this plot and I said that H-alpha and UV emission in star formation regions is quite often obscured by dust and re-radiated infrared. So my question is, can it be that where there is an outflow, there's also, by just coincidence, there's also a lot of dust, and we are looking at obscure star formation? And there is actually a very good reason. We have seen this before in submillimeter galaxies. This is actually the ALS survey, what Bitten was talking about last week. And the image, this is from TC, from Chan 2017 and 2020. And what you see again, narrow line H alpha image on the background, but now the contours are actually ALMA band 7 continuum data. And you can see that there's an anti-correlation between the ALMA data, the dust continuum, and your H alpha, because the dust is actually obscuring the star formation. Second part that I'm also want to know, all those quasars that I show were an example of negative AGN feedback are actually very luminous quasars, one of the most luminous AGNs in the universe. So what about normal galaxies? And we have perfect tools for this. It's called CMOS AGN survey at high redshift, also known as CASZ. Not very imaginative name, but does the trick. It's a guaranteed time observing by Durham on CMOS, which is an IFU unit on the VLT. We target 256 AGN in deep fields like CDFS, UDS, and Cosmos. And that's because they have loads of multi-wavelength data that we can use. And we are looking at redshift 0.8 to 2.6, so still high redshift. We observed H alpha or O3, and we have an overlap of some targets where we observe both emission lines. And because there's so much deep multi-wavelength data, we can actually do full SED decomposition and actually characterization of the stellar masses of these and star formation rates of these systems. So I selected something from this sample, and the way the selection process out of those 256 galaxies went is that we want both H alpha and O3. Great. That means redshift 1.5 and 1.2 to 2.5, given the way the CMOS can be set up. We need high signal to noise of these observations because we want to map them. So that's, and we also have some archival symphony data that we added, which is another IFU on VLT. But what we did differently compared to previous studies is we said, okay, we also want high resolution, which is by our standards, anything less than 0.6 arc second. I know it doesn't really seem that high resolution compared to other studies, but for our work, it's basically never has been done, of ALMA dust continuum. And when you put all these constraints on your sample and actual selection criteria, you ended up with 8 sources. Well, that's way less than 256 sources that we started at the beginning, but this is the best data to study effective AGN feedback at high redshift, because you have obscured star formation, unobscured star formation, and your AGN outflows. You trace all 3 of them. So these are, let's go over the results of my study. So this was done, this is the narrow H alpha on the bottom, and you see the contours, the red contours is the dust emission. And what the centers of the H alpha is the blue bit, and the centers of the far infrared is the red dot. And you can see that we have wide morphologies in both H alphas and the far infrared emission. So sometimes they are actually on point, they are bang on the top of each other. Sometimes they are miles apart and they are very anti-correlated. So actually this is where you need both tracers at the same time to study all the star formation in this host galaxy. And sometimes they are just a little bit offset, but they are so big that they are still relatively co-spatial. When you look at it from more statistical point of view, actually looking at the individual, actually look at the sample as a whole, you see the offsets between the the unobscured star formation and obscured star formation, or H alpha. Then we realized that 5 of our 8 targets have significant offsets between the obscured star formation dust and unobscured star formation, your H alpha. And when you look at your the sizes of the individual star formation tracers, then you realize that actually dust tends to be way more compact than H alpha, than your unobscured star formation, which is similar to what submillimeter galaxies actually are. So it seems that this is something they have in common. But overall, the result is that you must have multiple star formation tracers to trace all star formation in AGN host galaxies. So what happens when we add the outflows, right? What happens if it's like, okay, we know that we have all the necessary star formation tracers we need, and we add the AGN outflows, AGN-driven outflows from the O3 emission line in white contours. And overall, well, we don't really see any major cavities in which the outflows actually would fit. Usually there are just smooth 2D Gaussian kind of distributions of the star formation. So you see all the different shapes of the outflows, but nothing that and all the different shapes and morphologies of the star formation traces, but nothing really significant indicative of AGN, of some suppression of AGN, or suppression of star formation, sorry. So here is one detail where you see they are basically all co-spatial, nothing. Here's another example where they actually lie sort of on top of each other. The H alpha is way more extended than the outflow or the dust. And then we come to ID6, and ID6 is actually the object from Cressy 2015. It's the XID 2028. It's sort of on the edge of whether it's a moderate luminosity AGN or a quasar. And what you can see that even though when you measure where the peak of the outflow is, it's massively offset compared to the star formation tracers. It's the green point off on the right plot compared to the blue and red. Actually, the outflow is so big that you don't really see any sort of lack of, that you don't see any suppression of star formation. Now, you might wonder, why do the narrow H alpha maps, the images, actually look so different? And this comes to the data reduction, because we believe that we actually have their cube. They were so generous to send us their cube, their data reduction version, that when they were stacking the individual frames, they offset them by a couple pixels. And that's actually creates the arc that you can see in the top left image of sort of two different peaks, the star and the A. But we don't believe it's actually a genuine morphology of the galaxy. So this is a sneak peek now to what I have been trying to figure it out in the past several months since I submitted my PhD. And what about the high luminosity quasars? And that's because we actually went back and we got ALMA data for all those other quasars that were in the literature that showed some sort of a suppression of suppression of star formation by AGN outflows. And on the top panel, the top row, you can actually see my reanalysis of the narrow H alpha image. That's actually the image, and then the red contours are the ALMA dust contours. And what you can see is that, number one, compared to what they have, the other studies, what they have done on the bottom, I don't really see any sort of cavities in the narrow H alpha emission. And then secondly, even if you would say, okay, this is where we have disagreement, the ALMA dust continuum always fits in right into those cavities. And therefore, even if the cavities are real, there's still star formation, it's just obscured. So we don't believe that this result actually stands anymore. I'm now in the process of, I've actually redoing the analysis on the outflow, so I can have also my own outflow mass added, and hopefully it should be submitted soon. So conclusions overall, the talk of the second part and overall. H alpha doesn't always trace star formation in a galaxy. We need additional tracers to map obscured star formation. ALMA does a great job of this at high redshift. There's the reason why we think this is that there's a significant difference in both sizes and locations of the obscure star formation. They are probably not even tracing the same star forming regions, which is very important. There's no evidence that AGN-driven outflows are instantaneously suppressing star formation. It seems that AGN feedback is more subtle. There's one caveat worth pointing out, is that we have a resolution of the 0.5 arc seconds, which at redshift of 2, that corresponds to roughly 4 to 5 kiloparsecs. Now, low redshift studies, which I didn't really focus on, can potentially see some minor suppression of star formation on the scales of a couple hundred parsecs, but nothing as significant as suggested by the previous studies at high redshift. So AGN feedback is more subtle. It's, you probably we need to look at it statistically. For example, is there any sort of statistical evidence that higher velocity outflows are suppressing star formation? So we need to do it. We need to compare the distributions of sort of non-outflowing AGNs and outflowing AGNs and see what it does. And also, and I think this is what will happen, what we need, is we need to look at the cold gas supply. Is AGN completely destroying the cold gas supply that's then needed for star formation? Is it just warming up? What is it doing? We don't have any sort of systematic studies of doing it, and we should definitely look at it. Oh, and one last thing. Great things when you combine multi-wavelength observations. If you combine ALMA with something else rather than focusing on one type of observations or one emission line, you do a full range of emission lines. Then great things happen, and we should do it. Okay, that's the end.
Great, thanks very much. Give Jan a round of applause. So, does anyone have any questions they'd like to put to Jan?
Yes.
Yes, Alessandro, go ahead.
Yes. So I would like, again, like I did in the previous case, to congratulate very much Jan, because you have done a very, very good job and extremely clear presentation. So I have two questions, or actually two comments. So the first one, if you could put back your overhead, where you had the comparison between, where you were showing that it is not correct to identify just the means. You need to consider the distributions as well, which was log normal. So if you could put it again, there
Yes.
were, exact, yes. So in the bottom right, is this, I don't understand whether it is your fitted distribution or if it is just a sketch. Because, for example, how many parameters you have in your fitting methods? Because this is quite important. When you have nonlinear fitting like the one that you are showing here, and the topology of the space is very complicated. So the aim is, of course, to detect a global minimum, which gives you the perfect solution. But in reality, you may end up in very local minima or saddle points, so that you may have a lot of degeneracy in your solutions. So could you please comment on that?
Yes, this is a method on which you can possibly do 5 slides. So thank you very much for the question. It's excellent.
Thank you.
So first of all, there are 2 parameters. Once you assume the shape of the distribution, which is log normal in our case, there are 2 parameters that we are fitting. The mode of the distribution, basically the peak of the distribution, and then the width of the distribution. So we didn't feel like adding any more complex distributions like log normal, convolve with some power law or something, because just as simple as possible. Secondly, it's not a sketch, it's actually how we do it. It's actually the data and the fit. So actually, now that I have a mouse, I can actually point properly. So can you see this outline, the gray outline? That's the histogram of the detections that we have in the sample. What you see here, this outline, that's the histogram of the upper limits, because just because it's not detected doesn't mean that we don't have any data, then any information out of it. We still have an upper limit, and we can say it's definitely lower than that, right? And then the dash curve is actually the fitted distribution that we actually did. And the way you do is that you for the measurements, for your detections, you draw from some sort of a distribution where the distribution is centered on the value of your measurement, and then you have the width of which is your error on your measurement. And then for the upper limit, it's actually a log error function from which we draw, and we basically saying what is there is some sort of probability that the true value is sort of somewhere below the upper limit, and we repeated it a couple tens of thousands of times, and we see what happens. Like what we actually get, we get full posterior distribution of actually on the parameter of the mode and the width. So that's what I quoted in the rest of the plots. One way we tested it as much as possible is that I looked at the distribution in the simulation where we have 100% detection rate, right? By definition, you don't have any upper limits in simulations in this matter. And I just start putting their artificial upper limits, and I was increasing them, and I was testing the code, and like, do I still recover the shape of the original distribution, or is my code starting to sort of go completely bonkers and go on the side to some unreasonable parameters? Does that answer your question?
Yes, it's perfect. Very, 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 very good. Very, very good explanation. So I'm convinced. Absolutely.
Thank you very much.
Could you please put the conclusions again so I can just have my last comment?
Yeah.
Very good. Here you say something very, very, very meaningful. There is no evidence that AGN-driven outflows instantaneously suppress star formation. AGN feedback is more subtle. And this is as well a point that I made in a paper together with Cambridge Fatih in 2016. Maybe some other time when the bloody pandemic goes away, fades away, I can show you, we can discuss it. So there actually, our diagnostic was both the usual tumor parameter for gas, which people generally would like to find some kind of a minimum where you have star formation and then a very big jump to suppress star formation. And this is in fact what you get in NGC 1068, close to the circunuclear ring where you have a lot of star formation. But, so this, from an observer point of view, one would be extremely happy because you can prove with a simple dynamical model that star formation is actually quenched instantaneously by the AGN. But if you are using my stability diagnostics, which are more general than the tumor parameter, and which in particular take into account the self-gravity of the stellar disk, there you can see that this galaxy, this NGC 1068, is really a monster. It's the only galaxy in the universe that I've ever experienced with where the combined stability parameter for stars and gas is below 1. So this tells us exactly, as you point out, that AGN feedback is more subtle. It's not just enough to use a very standard diagnostic. You have really to dig into the problem. So I will be very, very, very happy when the bloody pandemic fades away, that I can show you these plots and we can discuss further. So thank you very much again for the amazing, nicely talk.
Thank you. There's just one quick thing. I would say, when I say AGN feedback is more subtle, I mean it in a very much high redshift sense of less than 4 kiloparsecs, which is what we have are sensitive to simulations, what other people suggest.
Yes, yes.
There's a caveat to that.
Yes, I understand. But there are as well several caveats, even at very low redshift.
Yeah.
Excellent.
Okay, Kirsten has a question?
Yes. So when you compare to the Eagle simulations, you say that the Eagle simulations have AGN and supernova feedback implemented. Can you explain a little bit more in detail about how it's actually implemented?
Yes, definitely. So AGN feedback, given you have a resolution of 10 to the 6 solar masses, you can't do any sort of a fancy accretion scale physics. So it mostly follows a Bondi accretion, and it's with a particle of a gas actually comes close enough to the particle that's the black hole. Then it basically they merge the particles. They just basically say, okay, done, they are now merged, and they re-radiate it based on the Bondi accretion equation, that energy that would normally sort of happen over the next couple of computational steps. It's all a radiative feedback. So some simulations, like illustrative simulations, use a sort of if it's a low accretion mode, then sort of there is not many particles around. Then it's a sort of more of a radio sort of a kinematic feedback. And then at some point, once you go over some threshold, which is a massive unknown actually, then you switch to a radiative feedback where you just re-radiate the energy. In Eagle, they simplified it to just simple radiative feedback all the time. I would love to do one comparison between Eagle and Illustris and all the different prescriptions of feedback. Also Simba simulation, because they try something new as well. That's a simulation in Edinburgh. When it comes to star formation, again, it's quite simplified, is that once a particle actually cools down to a sufficient level, then it goes through a very simple prescription that it's actually starts forming stars at certain rays, which is given by the amount of particles around it, which simulates basically the pressure and also the temperature of the particle. And then at some point, there is another relatively simple prescription where, again, the feedback hits roughly, I think, a couple million years afterwards, a couple steps later, where they start re-radiating some of that energy, heating the particles around it, how you do a supernova feedback. So they are, I would say, for people who do zoom-in simulations, these are relatively simple prescriptions. But on the other hand, you just have limited the resolution. And until we do a next generation of supercomputers, we might not be able to improve that much.
Okay, thanks.
Okay, great. Suzanne has a question.
Yeah, thanks. Very nice talk, Jan. I'm just going to keep on nagging about my obscured concerns. And that is, of course, as we see in more nearby systems, we see also obscured outflows that are not detected in the outflow. Also that obscured activities may look like star formation, but it's actually not. So I'm wondering, I have a general question, how this could be considered both in the simulations and in the observations, how we can take this into account. Because of course, we know that obscured growth, nuclear growth of supermassive black holes is probably more common than the unobscured ones. So the question is, how can we take that into account in your work?
I
It's
don't.
a very broad question, I know.
Unless you do zoom-in simulations, you can't really take this into account in the cosmological simulations. Because the simulations don't, there was something called a thermal floor in these simulations, and basically they don't allow the gas to cool below certain temperature, which is actually, I think, over a couple thousand degrees. And the reason is that then your particle would be actually way smaller than what you can simulate. So you actually never simulate even molecular or warm atomic gas, which is such a shame, because I think that can help us the answer. So unless you do zoom-in simulations, I don't really see a way we can currently do it with cosmological simulations, which is a shame. I really want to.
So this is not just a matter of you know, improving the models or improving the computer capacities. You say this is a fundamental problem in the simulations.
It's a fundamental problem in the simulations, but it comes from a lack of computing power. It's a fundamental, I don't know if I'm expressing, it's a fundamental problem, but we can solve it with better technology and money.
Yay.
We don't have both. We don't, but, and by that, I mean like order of 100 faster a computer might help us, I think.
The thing is, I'm curious because we do see feedback that is not detected in the optical, in the molecules. And this is a very interesting, I mean, we're just at the very beginning of exploring this, right? So it's extremely interesting to see how that would impact both the interpretation of the observations, but also the modeling work. But we can talk more about this offline.
Yeah. Okay, Frederic has a question?
Yes, quick one maybe. So throughout your talk, or until now, you have referred to AGN as a whole, I guess based on the optical properties. But I'm wondering about the presence of different types of AGN, like for example, BLux and flat spectrum radio quasars, FR1, FR2, and whatnot, in your observational sample, and how these different types may have different impacts on the star formation, and if that's measurable at all.
So that's a whole of a Pandora box that everybody tries to avoid on some level. First of all, when we look at the statistical studies, I don't believe there is any sort of results of a study that will show that, for example, type 1 to type 2 AGN, so those that those where you can see into the accretion disk and those that you can't, where you would see that they have different effects on the AGN. Because as far as we know, it's all about orientation, not necessarily about, it's about orientation. It's not necessarily about any sort of physical changes in the AGN.
Well, it can also be
you see more often that outflows are more seen in type 1, but that's probably because you are actually looking into the accretion disk, so it's easier to actually find the outflow, but again, nothing more like a physical difference. When it comes to the radio, that's a whole unexplored thing that we should really focus on. You do it especially at lower redshift these days with Miranda Jarvis, Stephen Molina, basically the sort of PhD students of Chris Harrison, who is now in Newcastle. And you see in simulations, for example, show that actually it's the radio mode, the radio AGNs that do most of the damage to the galaxy rather than these outflows. Unfortunately, doing at higher redshift, radio studies at higher redshift is just very hard. So we have a couple of ideas how to progress it, but it's something we should definitely focus on.
And the sample, your observation sample, is it biased or towards some AGN type, or is it a uniform distribution of any type?
So this study, or whatever, where's the nice overview? This study, the 8 AGNs, same amount of type 1s as type 2s, roughly. When it comes to the first statistical study, the ALMA one, the ALMA Eagle, that was 50-50 as well on type 1, type 2. When you look at these quasars, these are the most luminous quasars in the entire sky. One of the like top 100, top 10, whatever. These are all type 1 quasars. The one on the right is a massive radio source of like 30 millijunsky at 1.6 gigahertz at redshift 2.5, which is like, oh my God, so bright. These don't really have any measurable radio properties that we can do. They are not really detected in anything. So these are the extremes, and that's why we decided to go for the moderate luminosity AGNs ones, sort of the more typical ones. And when we look at the more typical ones, I think we have couple that are detected at radio, and equal amount of type 1s and type 2s. In terms of radio morphology, FR1s, FR2s, we have no idea of knowing at redshift 2. We need very high resolution studies for that.
Thanks.
Great. Any more questions? Anyone want to raise their hands or unmute themselves or say anything in the chat window? Nope, I see nothing. So I'm going to conclude that the seminar is over now. So let's give Jana another round of applause. And we don't currently have a speaker for next week yet, but we'll let you know if that changes. So thank you, everybody, and have a good rest of your day.
Grazie.
Goodbye, thanks.
Arrivederci.
Bye.
Bye.